So in today's class, we will discuss introduction to quantum physics. Okay. So let me tell you one thing. This is a theoretical topic and we will get some numericals in the exam. So before the numericals, you must know what basically the quantum physics is and how to solve the numericals. Okay. So there are total 3 videos for this, part 1, part 2 and part 3. So we will start with part 1 now. So as it is mentioned here, an object at any temperature emits electromagnetic waves. Okay, this is very important. If there is any object in the room, anything, okay, any temperature, it always emits electromagnetic waves in the form of thermal radiation from its surface. Okay, so basically like any object, like a table, table, duster, a window, anything, it always emits a electromagnetic waves. Okay, so the characteristics of this variation depends on the temperature and properties of the object surface. Okay, now what is black body? So if you have seen, like when we do any reactions or something, we see this is a black box. Okay, black box means there are some components in it and we are passing some input and we are getting some output. So it's nothing clear that what is inside the black box. Okay, so same, it is a black body, like the ideal body. Okay, so I'm removing this. Okay, so what is black body? Now look at here. It is an ideal system that absorbs all radiation incident on it. Okay, so suppose this is a black body here, black body. Okay, any radiations which are coming through, like this, like this, like here, 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 anywhere, it absorbs all radiation incident on it. But this is a ideal case. Okay, practically it is not possible. Okay, the electromagnetic radiation emitted by the black body is called black body radiation. Okay, and the radiation what it emits is the black body radiation. Okay, so now, so there are two findings. The first one is Stephen's law. Okay, what is a Stephen's law? The total power of the emitted radiation increases with temperature. So remember, power increases if the temperature increases. Okay, this is a point to remember. If temperature decreases, then power decreases. Okay, so this is basically the Stephen's law. And this, there is a formula which you need to remember. You can get the numericals based on this formula. So power equals to sigma A e t to the power 4. Okay, now where P equals to power in watts radiated at all wavelengths. Okay, remember it's on all wavelengths. Sigma, it's basically, it is 5.670 into 10 to the power minus 8 watt per meter square multiply Kelvin to the power 4. It is a Stephen Boltzmann constant. Okay, A equals to surface area of the object in meters, E equals to emissivity of the surface, and T equals to surface temperature in kelvins. Remember, always the temperature is in kelvins, not the Celsius. And E equals to 1 for a black body. If it is a black body, then E equals to 1. Okay, but if in exam you get the numericals based on it, then you will have that formula in your formula sheet and you can directly use the formula. Okay, so the first is Stephen's law. What we have studied so far is the basically what are electromagnetic waves. Every body in the space just emit the electromagnetic waves. What is black body? Black body is an ideal system that absorbs all the radiation. What is black body radiation? Which is emitted by the black body. Okay, now the two findings, the first one is the Stephen's law. Okay, and second one is Wien's displacement law. What does the Wien's displacement law states? It states that the peak of the wavelength distribution shifts to the shorter wavelengths as the temperature increases. That means if I am increasing the temperature, okay, I am increasing the temperature, then what happens? Wavelength distribution peaks. Suppose it is a wavelength distribution like this, okay, so this peak will shift to the shorter wavelength like this as the temperature increases. Okay, so this formula you need to remember, like I will explain you again. This is suppose a wavelength peak like this, but when we increase the temperature, then this peak will return to a shorter wavelength. So this is Wien's displacement law. Okay, and the formula is lambda max T equals to 2.89 into 10 to the power minus 3 meter Kelvin. Okay, lambda max equals to wavelength at which the curve peaks. So suppose this is like this one, so this will be my lambda max. Okay, and suppose if it is, so wherever the curve is at the peak, this is your lambda max. Okay, and T equals to absolute temperature of the surface. So these are the two formulas which we will be using in the numericals. Okay, now the first numerical. Find the peak wavelength of the black body radiation emitted by the human body when the skin temperature is 35 degrees Celsius. Okay, so first of all, we will see what is given to us. So given is temperature T equals to 35 degrees Celsius. But remember, this temperature is in Celsius, so we need to convert this temperature into Kelvin. So what we'll do? 35 plus 273 equals to 308 Kelvin. Okay, now what we need to find out? What we need to find out? Peak wavelength. Okay, lambda max. So what formula we will use? So I am writing here calculations now. So formula we have this lambda max T equals to 2.898 into 10 to the power minus 3 meter into Kelvin. Okay, so for lambda max, what will happen? 2.898 into 10 to the power minus 3 upon 308 Kelvin. Okay, so if I will calculate it, what will happen? Let me calculate. So it will be okay, 9.41 into 10 to the power minus 3 into 10 to the power minus 3 meter Kelvin. So it will be 9.41 into 10 to the power minus 6 meter Kelvin, or I can write 9.41 micrometer Kelvin. Oh, Kelvin to Kelvin we can just cancel out like here. Okay, so if it will cancel, then K we just removing it, and then in the final answer is this one. So this is my answer and I am writing answer here. Okay, so this type of numerical you can get. Now question number 2. Find the peak wavelength of the black body radiation emitted by the tungsten filament of a light bulb. Okay, sorry. So how to solve this? Again we will use the same formula. First of all, we will see what is given to you. Find the peak wavelength, and okay, given is temperature, which is 2000 Kelvin. So now the temperature is given to you, okay, in Kelvin. No need to transfer, no need to change it into Kelvin because it is already given. To find lambda max, and we know the formula calculations. We know the formula lambda max equals to 2.898 into 10 to the power minus 3 meter Kelvin upon T. So when we are putting everything in the formula, we will get 2000 Kelvin, Kelvin to Kelvin cancel, and when we will solve, we will get 1.45 micrometer. Okay, so this is my answer. Okay, so these are the type of questions you will get. Now, question number 3. A 2 kg block is attached to a massless spring that has a force constant of K equals to 25 Newton per meter. Okay, so it is given there is a 2 kg block which is attached to a massless spring. Okay, now the spring is stretched 0.400 meter from its equilibrium position and released from rest. A, find the total energy of the system, and B, assuming the energy. Okay, B we will do later. So first we will solve the A part. Okay, now first of all we will see there is a spring like this. It is stretched to how much it is given? 0.400 meter. Okay, it is a massless spring. Please remember, when you do any physics question, you need to visualize it. You need to make the figure always. Okay, now we will write evaluate the total energy of the block and spring system. We will find out the total energy. Okay, so E equals to half Ka square. We all know this formula. Okay, so now it will be half. What is K? Spring, what, see, like K equals to 25 Newton per meter. It is given to you here. So we will write 25, and A is given to us 4 meter square. So when we calculate it, energy will come to 2 joules. Okay, this is our energy. And from where this formula came, if you remember, we did the spring system. Suppose if it is x, now it is x plus delta x. Okay, and it is half K delta x square. It is for the spring when we use the energy thing. Suppose the spring is having the x constant, but now it is stretched to delta x. So delta x will be very small in comparison to this. So it will be K delta x square. Now, this is the A part. Find the total energy of the system and the frequency of oscillation according to the classical calculations. So energy we have already found out. Now we need to find out the frequency. How we will find out the frequency? So for frequency, you need to remember the formula F equals to 1 by 2 pi under root K by M. So these formulas will be given to you in the formula sheet. So it will be 1 by 2 pi. K is 25 Newton meter. It is given, and mass is 2 kg. Let's see here. A 2 kg block. Look here. It is given a 2 kg block. Okay. So mass is 2 kg. When we solve this equation, we will get 0.563 Hertz. So this is my frequency of oscillations. Okay. So this is my answer and this is my answer. The two things which are asked in A part. Now what is the B part saying? Let's see the question again. Okay. Assuming the energy of the oscillator is quantized, find the quantum number n for the system oscillating with this amplitude. Okay, so we need to find out the quantum number n. How to find out the quantum number now? So quantum number n equals to En by hf. I will tell you now from where this formula came. Okay, we know the normal formula. When we talk, energy equals to h nu. Okay, this is the normal formula we know, and we know c equals to nu lambda. So you all know c equals to speed of light, nu equals to frequency. Okay, we can write f or nu, anything, and lambda equals to wavelength. Okay, so this formula is a standard formula. You all know this formula. C equals to nu lambda. Now suppose if I need to find nu from this formula, I will write C by lambda. Okay, so now if I'm going to put this value here in this formula, what I will write? E equals to h, and what is nu? Nu equals to C by lambda. Okay, so that means if I need to find out En, what I can write? N h C by lambda. It's for n numbers. Okay, so quantum number n, if I need to find out n from this formula, so what I will write? En lambda equals to nhc, and n equals to n equals to En lambda by hc. Okay, and now what is lambda by c? Look here. Look here. So if basically c by lambda or lambda by c, anything you can write. So 1 by nu equals to lambda by c. Okay, and nu equals to f also we can write. So 1 by f. Okay, so I can write n equals to En 1 by f and h. Okay, now you can see n equals to En by hf and n equals to En by hf. So from this thing we get this formula. Let me tell you again. So E equals to h nu, this is a standard formula, and C equals to nu lambda. Okay, nu is frequency, lambda is wavelength, and C equals to speed of light. So what we can write from this formula, nu equals to C by lambda, and nu or frequency is the same thing, nu or f equals to same thing. So if we reciprocate it, then it will be lambda by C equals to 1 by nu. Now every value I am just putting in this formula. Okay, so it is E equals to h nu, then E equals to hc by lambda. Just putting all the values for En and then putting lambda by C equals to 1 by f. So we will get this formula. Okay, so now just put all the values in the above formula. N equals to En. What is En? Is 2 joules. It is given. We find out already E. H. The standard value of H is 6.626 into 10 to the power minus 34 joule second. Okay, and what is F? Frequency. We already calculated in the A part. It is 0.563 hertz. Okay, and when we calculate it, I will get 5.36 into 10 to the power 33. So this is my N. Okay, so these are basically A and the B part. For B part we are using this formula. For A part it is frequency. Okay, so I hope you will be able to do such type of questions, and we will take these questions in the in the class again. Okay, thank you.